So let's pretend that we're running a bicycle factory. And we're going to think of this in very simplistic terms. My oldest son used to work at a bike shop and learned how to fix bikes. And it turns out that bikes actually have a lot of pieces, right? But we're going to keep it really simple here. And we're going to say that in order to make a bike, you need 2 wheels and 1 frame. And that makes 1 bicycle. I'm going to write bike because bicycle's too long. 2 wheels and 1 frame. Okay? So if I have 50 wheels, how many bicycles can I make? 25. How did you do that? Because one bike has 2 wheels. So what you did in your head was you said you get 1 bike for every 2 wheels. That equals 25 bikes. You can do it in your head because you can picture bikes and wheels. They make sense to you. When we talk about moles of hydrogen and grams of oxygen, you go, ah! Or that's what your brain does. It really does make that sound too, doesn't it? 50 wheels will get you 25 bikes. Well, what if we had 50 wheels and 50 frames? How many bikes could we make if we had 50 frames? If we had enough wheels? 50. Because we get 1 bike from each frame. So 50 bikes. I almost wrote kites. Why? But if I had 50 wheels and 50 frames, could I make 50 bikes? No, why not? Run out of wheels, right? Because you can't make a bike without wheels. It just doesn't work. It's not a bike. So, what is limiting how many bicycles we can make in the factory? The number of wheels. If we had more wheels, we could make more bikes, right? So we say that the number of the wheels are the limiting reactant. If we think of this in terms of a chemical reaction, the wheels and the frame are the reactants, and the bicycle is the product. The number of wheels that we have available limits the amount of product. So this is the limiting reactant. So let's think about, I'm just going to erase some of these numbers here. So give me 2 whole numbers. 6 and 3. Okay. So, okay, I don't like those numbers. How about 6 and 5? If I had 6 wheels and 5 frames, how many bikes could I make? 3. So what you did in your head is you said, well, if I have 6 wheels, I can make how many bikes? 3. If I have 5 frames, I can make 5 bikes. But I can't actually make 5 bikes, can I? You're going along, you make 1 bike, you use up 2 wheels. You make 2 bikes, you use up 2 wheels, and you've used up 2 frames. And you make the 3 bikes, you used up all your wheels, production stops. Sometimes with chemicals, I ask a question like this, and a student will say, I can make 8 bikes. I'm like, well, that's a cool trick. Show me how you're going to do that. What we're doing is we're taking the amount of each reactant, and we're figuring out the amount of product that we can make. And then we're saying which one is smaller. The smaller one is the answer. Because in real life reactions, you usually don't have just exactly the right amount of everything. If you think about making pancakes, if you make a recipe of pancakes, or I've had to make pancakes when my football player boys had guys spending the night, and they wake up in the morning and they're like black holes for pancakes. And so you make like 4 double batches of pancakes and they devour them. You're making pancakes and you're making pancakes, and you run out of one ingredient, right? It's often something like the eggs or the buttermilk. But have you ever made a recipe where you used up every single ingredient you had just exactly the right amount? That doesn't happen, does it? Making sandwiches, making cookies, nothing happens like that. So in real chemical reactions, there is usually one reactant that limits the product. So that's what we're looking at in this section. So now we're going to think about this in terms of chemicals. If we heat a mixture of iron powder and sulfur, it produces iron sulfide. Here's a picture of that actually occurring. Here's the balanced chemical reaction. Iron plus sulfur gives us FeS. So here we have pictures. So if this is our starting mixture, we have 3 iron atoms and we have 4 sulfur atoms. Ooh, awesome. You're right. The problem is not that it's unbalanced. The problem is, I think, that I wrote the wrong thing, because this is a picture from the textbook. So yeah, that's wrong. I can fix it though. Watch this. This is so cool. There we go. Oh, better. Iron 2 sulfide. Thank you for catching that. So iron 2 sulfide. So we can take these 2 guys. Let's just circle them. So these 2 could make 1 unit of FeS, and these 2 guys can make a unit, and these 2 guys, what's going to happen to this sulfur? It's just going to sit there. It's not going to disappear, but it's not going to react either. It's like we're running out of wheels at the bicycle factory. What happens to the frames? They sit there until we get another shipment of wheels, right? So over here, we made 3 molecules and we had something left over. What limited the amount of product? The iron. Because the sulfur, there was 1 left. So here's B. Now we've got 1, 2, 3, 4 irons and 3 sulfurs. So we could pair those guys up, and these 2 and these 2. This time we have an iron left over. This time iron is the limiting reactant. We made 3 of these units and we had 1 iron left over. They always combine in the same way. Just like a bicycle always has 2 wheels, right? If you put 3 wheels on it, now it's a tricycle. So we can't just say, oh, well, we don't want this guy to be left out. We're going to let him form a group of 3 with these guys. It doesn't happen.
So just in the first one, the iron is the limiting one, and the second one is the sulfur is the limiting one.
I said that wrong, didn't I?
I'm just double checking.
Yeah, it is the sulfur in this one.
Okay, thank you.
I sometimes get things. So here, sulfur is limiting, and here the iron is limiting. No, that is, see, now it's just, we'll just rewind. The iron is limiting. The sulfur is in excess, is what we call that. And here, the sulfur is limiting. Oh my goodness. I'm used to looking at this in terms of equations, and then the pictures, I'm like, I don't know, I just lost my mind there. Okay. Are we all together now? Sorry, I screwed you up there. Okay, so we can do things like this. Suppose we heat 2.5 moles of iron and 3 moles of sulfur. How much product will form? Well, before the reaction, we've got 2 moles of iron and 3 moles of sulfur. and we've got none of the product. That should not be a capital E. And that should not be a capital E. Okay, I'll get over it. If we have 2.5 moles of Fe, how much product can we make? Balanced chemical equation, 1 mole to 1 mole, 1 and 1. We can make 2.5. You didn't see that. Nobody saw that. Anything else wrong in there? It's Friday afternoon, people. So from 2.5 moles of iron, we can make 2.5 moles of iron sulfide. From 3 moles of sulfur, and I agree, it's a little silly to write all this out, because it's 1 mole of FeS to 1 mole of sulfur, right? And so we could make 3 moles of product. But can we make 3 moles of product? No, because we run out of the iron. So when you have a problem like this, where they're giving you quantities of 2 reactants, you do 2 calculations. There are other ways to do this, but this is the most straightforward and easiest to remember. You do 2 calculations to find amount of product. You look at that and ask yourself, which one's smaller? Okay, this one is smaller. That is the answer of how many moles of product will form. Sometimes then they'll ask you to identify what's the limiting reactant. Well, this is your smallest answer. You go back to the beginning of that calculation. There's your limiting reactant. And so we sometimes say LR, limiting reactant. So this little table here is showing us that, yeah, we made 2.5 moles of iron sulfide. That used up all of the iron, and it used up 2.5 moles of the sulfur, and there's half a mole of sulfur left over. And it happens. There's leftovers. It's okay. Any questions? So let's do another one. A 5 mole sample of iron 3 oxide is heated with 5 moles of aluminum metal and converted to molten iron. Identify the limiting reactant and calculate the moles of iron produced given the unbalanced equation for the reaction. Okay. Balancing, let's see, 2 irons. So we need to fix that over here, put a 2. 3 oxygens. Hey, that's nice. 1 aluminum, 2. We can fix that. Okay, so we got a balanced chemical equation. And now it's telling us we have 5 moles of that one and 5 moles of this one. And it's asking moles of iron. Question mark, moles. The clue that this is a limiting reactant problem is they gave you quantities of 2 reactants instead of just 1. The ones we were doing in the previous section, they would have given us this or that, but not both. So they gave us 2 quantities. We have to do 2 calculations. And we're keeping it simple with these. We're doing moles, so we're just doing the center part, mole to mole. We don't have to deal with the grams or the liters or anything. So if I have 5 moles of Fe2O3, and I'm going to assume that I had plenty of aluminum, I'm just going to go from moles, plenty of aluminum, moles of aluminum, and I want to divide by moles of Fe2O3. Just so my units work out. And then I get numbers here. One of this, wait a minute. What did I do wrong? We're looking for Fe, right? So, okay, well that's not what I want. We can fix that. Fe. Yeah, I forgot where I was going. This is where I'm going. Wake up. Okay, so Fe. Moles of Fe, so there's 2 of those for every one of these. So that gives us 10. 10 moles of iron. And then we take, so that's this one. Then we take the other reactant, 5 moles of aluminum. The calculation follows the same pattern. We're going to the same ending, the moles of Fe. But now I'm dividing by moles of aluminum, so moles of aluminum cancels out. 2 iron, 2 aluminum. So this gives me 5 moles of iron. So when it says calculate the moles of iron produced, which of these 2 answers do I choose? The smaller one. This is the smaller one. What's the limiting reactant? The aluminum. It's the one that gave me the smaller answer. This is the limiting reactant. Now, on exams, we're doing multiple choice, so you don't have to worry about this. But on a worksheet, sometimes students will do this. They'll do that, and they're done. It's very good work, but you still have to identify the answers, right? So, when you get to 1A, you need to go with whatever your teacher says, but I tell my students it's fine to just do that. Just show me that you're choosing this one. Okay, any questions?